Hi, welcome to QSYS Control Quick Starts. My name's Jeff Perkins and I'll be your host today. In today's episode, I'm going to do my best to knock out some of those urban legends having to do with control frames. In this episode, you can expect to learn that control frames, or the frame rate, is the communication speed limit between the control engine and the audio engine inside of a QSYS core. Turns out, those two engines synchronize states at 30 Hertz. That's every 33.3 milliseconds. Additionally, scripts and control pins are generally not affected by the frame rate and generally run at as fast as reasonably possible. I know. Anyway, the key idea is that the frame rate is a thing. It does matter, but not everywhere that you think that it does. With that, let's dig in. Let's close that. And as I said, there are a number of urban legends and misconceptions having to do with the role of the frame rate and where it comes in and what does it do and how does it affect things. And I really do hope that this helps to clarify most of the muddy water. I've set up here an example for us. In fact, we're live on my core. I have a microphone, a different microphone actually, plugged in, and we're going to meter this thing, and I'm going to turn on this particular script, and let's get that going so we can see it. It's thinking. That's a thing. All right, here we go. Let's move this over and split the screen accordingly. Doop-a-doop-a-doo. And here we are. So we have a very simple, right? We're bringing in a microphone. As you can see here, we're metering it in real time. I happen to be running it through a meter. And then I am bringing it in, let's get that out of the way, into a very simple script. All it has is a knob, and it's reading the decibels. And as you can see here, every time I talk, the input, the input meter on the microphone is registering. The meter in the metering component is registering, and we are getting data flowing into our knob. As you can see here, our debug window is going nuts. But here's something very important to notice. I'm talking continuously, and in the real world, we know that there is indeed a signal and it's going up and down basically all the time. Let's stop this script for a second and make some observations. One of the things that I really want you to see here is, well, look at those timestamps. And as you start doing some of the deltas on those timestamps, what you'll see is that, we're getting data approximately every 30 Hertz. That's right. What's happening here is the data is coming in, and it takes about, well, 30 Hertz in between those. Now, there's no faster than 30 Hertz. Let's talk about why that's going on. I'm going to close this. And I've got some pictures to show you. In fact, let's close this and close this and close this. And let's think about this scenario. Let's think about the audio engine updating the control engine, because technically that's what we are observing here in this particular moment. In this particular picture, and let me shimmy this over here, what you can see is that in the real world, right, data is going like this, right? The meter is doing all kinds of things, but we're only getting updates in the control engine, i.e. every time I printed that debug window, I only got an update as fast as 30 Hertz, every 33 milliseconds. Here's how you should understand this picture. Basically, we have two engines running inside of the core. The audio engine, which is running ridiculously fast, and then the control engine, which is running really, really fast. I guess if I should turn those around, I should have made a Spaceballs reference here and said that the control engine is running ridiculously fast and that the audio engine is running ludicrously fast. If you don't know about Spaceballs, shame on you. You should go check that out. Anyway, here's the big idea. These two engines, they're always running and they're running independently, but because QSYS control invariably at some point is going to interact with the DSP side of the DSP, well, those guys need to talk to each other, but they don't need to talk to each other continuously. So a decision was made a long time ago to decide they ought to talk to each other every 30 hertz. That seemed to be a good enough answer, and that is the answer. The two talk to each other every 30 hertz. Now, say talk to each other. What I really mean is they synchronize states. So let's take the metering example we have here. On the audio engine side, it's continuously changing, as you can see. But every control frame, i.e. every 33 milliseconds, whatever the value is, gets pushed through to the other side. And in this case, the control engine updates and stays at the minus 20 decibels. And notice how in the audio engine, everything is continuing to move, but the control engine value stays at negative 20 until the next control frame. At the next control frame, data is sampled, and the value of, in this case, something like minus 12 dB passes through, and then the control engine updates and maintains that negative 12 dB for the next 33 milliseconds. At the 66 millisecond mark, we sample again, the minus 5 passes through, and the control engine instantly updates and stays where it is. And as you can see, we kind of get this stair step on the control engine side. All right, let's reset. What's going on? Things are dynamically changing in the audio engine, and they're being reflected in the control engine every 33 milliseconds when they line up. Okay, now, it's also possible to do things in the opposite direction. For example, if I had a gain or something, I could, in turn, send gain values. I'm just making that up, right? Any control value that is going to affect the audio engine. We can, let's just pretend it's a gain. I can take that gain and I can go full preschool on it and just go up and down, up and down, up and down, up and down, super crazy style, okay? But the same story applies. Every 33 milliseconds, the level's value gets passed from the control engine down into the audio engine. And so let's start here at 0 milliseconds, right? Just when we start paying attention, the level of minus 20 passes through and it stays at minus 20 because presumably that's where it was. But let's watch what happens at the 33 milliseconds. At the next control frame alignment, we sample from the control engine that the level is supposed to be minus 15. That value then passes down into the audio engine, and notice what happens. The audio engine starts moving from minus 20 to minus 15, and it ramps nicely across the width of the control frame, right? You don't get those stair-step jumps in the audio engine because we might actually hear that, and that wouldn't be good. So you end up getting a nice linear move from one value to the next value to the next value. So let's continue the story. At the 66 millisecond control frame alignment, notice that the level has now gone up to positive 10. That value comes through down to the audio engine, and the audio engine responds by beginning to transition from minus 15 to positive 10 over the width, right, over the time interval of the control frame. At the 1 second mark, right, at the 100 millisecond mark, this is what our fourth control frame that we've considered, we have a new level. It is less. We're now at plus 5, and you can see here that over the width of that control frame, the audio engine is tapering off to that new target value. This, my friends, is really what we mean when we talk about the control frame or the frame rate. Really, truly, 99.9% of the time, what it's having to do with is it's having to do with the intercommunication between those two engines. And that's really it. Now, there are a few other things that occasionally you will see that comes out at the control frame. I can think of like ramp time. When you set a ramp time, what happens is things move and they naturally, the way QuickSYS is coded way under the hood is it makes those adjustments at the frame rates, but that's a happenstance. And it's a holdover from the fact that, right, we started as, well, everything we did with control had to do with the audio engine. So naturally it should move that way. The reality is well, nowadays we use gain knobs associated sometimes with other things like DMX light values. And we can turn knobs but the end result is, at the end of the day, things moving over 33 milliseconds actually is pretty nice from the human experience. So it works out just fine. Other places where you might see this 33 milliseconds pop out is in control links, for example. Again, these are because those are things that have existed for a long, long time. And at the end of the day, it's okay. Now, where does the control frame not really come into play? Generally, when I am working inside of a script, scripts run as fast as reasonably possible. For example, let's take a look. Is that still recording? It is. Okay. Let's take a look inside of the timers here. Let's look at this particular script. And here we go. I've made a little silly timer. It's named timer. I wasn't creative this time. And I've set a counter. Counter is 0, and we're just incrementing counter and printing it every time. And notice what we've done here. We have set the timer to run at a really ridiculous rate here, right? That is 10 times a millisecond. Let's stop the script and let's see what has happened here. On my core, notice I am indeed getting the timer to run at 10 times a millisecond. My friends, the control engine runs really, really fast. As I said, ridiculously fast. The audio engine, ludicrously fast. But the control engine, ridiculously fast. I can, on most cores, in fact, I haven't tried it on every core, but you can get really, really, really fast timer responses. Here we are, 10 times a millisecond. That's stupidly fast. Okay. Now a caveat here, because you might try this at home on your computer. You can do it in emulation, but I'll tell you, when I do it on my own computer will only run it basically every millisecond, which is still plenty fast enough almost for every possible situation. The reality is different machines, right? Different computers, and my laptop is a different machine, a computer, than the Core Nano, which is a different from the core mode of an NV32, which is different than the core of a Core 110. They all have their own particular sets of equipment under the hood, and so you can definitely expect slight differences in those levels of performances. But again, look at this. We're talking about the ridiculous edge of things, okay? You do normal things, you're gonna be fine and you'll never see a difference. Okie doke. All right, that's enough about that one. Let's talk about where we used to talk about control frames being the issue, but we actually were wrong, right? It was an urban legend or misconception. Let's talk about loops. Here we are. Here is a loop. We have loops in, here's what I've done. I've written that B is false, and then for 5,000 loops, I have set B to be not B and printed it and run it. Now look, I basically did 5,000 loops, so far as I can tell, within a millisecond or two of each other, right? My debug window only goes back 100 lines. So the last 100 of them was able to get done in within 3 milliseconds. So again, the control engine, it runs ridiculously fast as reasonably possible. And there's that. All right, now that urban legend, right? Things where we thought things would was actually related where they're not. Let's take another look at another script. Here we are. And ye old classic here, classic while loop. This while loop, there's nothing wrong with it. We set the counter to be equal to 1. We wrote the while loop that says while counter is greater than 0, do the following: increment, print, and then end. And notice what happens. My core made it 22,000 something times around the loop before I got some nasty red letters. Max execution limits exceeded. What's going on here? What's going on here is exactly what it says it is. It's a max execution limits exceeded. It has nothing, 0% to do with control frames. It is simply exactly what it says it is. The constructors of the Lua implementation for Q-SYS, I'm talking about the engineers, the designers, they set an arbitrary limit way back in the day of, you know, it's kind of hard to know the difference between a loop that doesn't end, i.e. an infinite loop, and a loop that just is going to run for a long, long, long time. And let's think about it. Logically, there's nothing wrong logically with infinite loops or loops that run for an extra long time. But in the real world, we run code on machines, and machines have finite resources. And if we're not careful to tend to those finite resources, well, then bad things happen. So let's think for a second. If we never had this execution limits exceeded error, then presumably this script would just run and run and run and run and run, and counter would get bigger and 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 bigger, and then it would overflow it's whatever was allocated for it in memory, and it would just keep getting bigger, and it would just eventually like just take over everything. Haven't you ever opened an Excel spreadsheet that just got stuck, and then finally the response was the computer just rolled over and crashed? That's what happens if you don't prune loops that don't close in a timely fashion. We prune the loops if they don't close in a timely fashion because, well, 2 really good reasons. One, we want everybody to have a fantastic audio experience. We don't want the audio to start, right? You would be so frustrated if your audio system started hiccuping and burping and glitching out like that. We want to prevent that. We're taking some reasonable measures to stop that. Secondly, you guys know that a lot of the times cores can find themselves to be centerpieces of life safety systems, and we need that audio system to be working when it's called upon, when it's deployed in those ways. All right, we don't want any troubles from that perspective, and so we are simply trying to protect the health of the whole system as a whole. And besides, you now know that this can happen. And then secondly, that's a lot of loops. It's a lot of loops. You probably 99.9% of the time can get done what you need to get done in less loops. So maybe look into that. If you ever see this error, know that it's related to a loop not closing in a timely fashion. When else does this usually come up? I've seen some of you like to make really, really, really big tables, and that can get hung up sometimes. Like, but again, right, the things I saw that you guys were doing was you were really trying to press the boundaries to find things. So again, 99.9% of the time when you're doing normal things, it's no problem. The other place where this might come up is if you're doing really big JSON objects, JSON strings. We have 2 libraries. We have the JSON library and the rapid JSON library. If your JSON is too big and you're starting to run into these kinds of errors, change libraries. Use the rapid JSON library. It's actually built for using really big JSON objects, which I guess is also redundant because JSON has the word object inside of it. I know, right? It's the ATM machine. I get it, but whatever. Anyway, there you go. So max execution limits, they have nothing to do with control frame rates. They just don't. It's an arbitrary limit. It just is. Sorry. Okay. Lastly, let's look at this as well. The frame rate, really, generally, they don't affect the control pins either. I've made some pretty silly demonstrations here. I'm going to open the first one here called the infinite domino. And let me tell you, when I was building this file, this one's only run out to 10, but I have run it out to like 300 or something. It was too big for my screen. It was hilarious. Anyway, let's look at it. And let's open this file. And let's move this over. Boop-a-doop-a-doo. All right, I'm sure my head is in the way, so let's bring this over. So basically, I have a series of toggles, and because of the way that I've wired them together, it's basically going to be a set of dominoes, right? You know what I'm talking about. You guys were all children at once, right? You probably don't know how to actually play dominoes, but everybody knows how to stack dominoes and go boop and watch them all fall down. Very simple script. And basically all we're doing is I've written an I-pairs loop on this array of controls so that it will print out which domino fell, and did it go from true to false or false to true, etc. Here we go, poke the button, and boom, there it is. Notice, hey, look, all 10 of them fell within basically the same millisecond. Guys, control frames are not in play here, right? That 33 milliseconds, not in play here. We set off 10 dominoes basically within the 1 millisecond. You can go crazy and make your own version of this script and run it out longer, and you'll see, yeah, for sure. This thing's running much faster than 33 milliseconds. Okay. Now, one last example, because for those of you who are like, yeah, but that was just all within one script. What about in between scripts? I gotcha, right? And again, I could have done this much more, but let's fill this out. That's domino number 4, domino number 3. Again, what is this? This is basically toggles run into each other, and we are simply going to have them do their thing. And here we go. Doop-a-doo, get that in there. All right, and one last domino number 1, and we'll put it down here so that we can get all of this. Now, I guarantee at this point in filming, my head's in the way, but we'll see what happens. All right, here we are. Dominoes 1, 2, 3, and 4. I'm going to fire them off, and you're going to see, boom, look at that. The first one went off at 7:14, and the other 3 basically instantaneously, all within the same millisecond. Again, you can build your own. You can take it out as far as you want to go. You'll see that those control pins update much, much faster than the control frame rate, right? It's not 33 milliseconds. They run as reasonably fast as possible. Now, is that an exact answer? No, it's not. Is it the most technically correct answer? Yes, it is. Do you want a better answer than that? I'm sorry, it doesn't exist. So as we are wrapping up here, what's the big idea? Control frames, i.e. the frame rate, is indeed the speed limit of communication 99% of the time. We're talking about that when we're going back and forth between the control engine and the audio engine, right? That's just when they synchronize to pass data, okay? Pretty much everything else we do over on our side of the fence in the control engine, it's running ridiculously fast. Audio engine runs ludicrously fast, but on the control side, we're running ridiculously fast, and going as fast as reasonably possible. Yeah, as fast as reasonably possible. And with that, I really hope that we've cleared most of the mud from the water. Let me know what I didn't clear up for you. With that, we'll see you real soon. Take care.